Problem 5. Find all values of the variable that satisfy the following inequalities. So here we have a logarithmic inequality. How do we approach inequalities? There are several ways, but what would you suggest we do here?
I would suggest we first take this equation and turn it into equal sign.
We take this inequality and look at the equality. Good.
So from here we can turn it into, because here we have 3 to this power.
3 to this power. We rewrite it in exponential form.
3 equals 4a minus 7. And then we'll have 4a minus 7 equals 27. So we add 7 to both sides. Now we have 34.
So A.
And now we divide both sides by 4.
And reduce. Reduce when you divide by 4.
Well, 8.5.
We can do that, or we can also have it as 17 over 2, which is 8.5. All right, so that's the equality, but how do we know the A itself? Should it be greater or smaller? Because that's the boundary. It will hold the equality sign right here.
So let's try, if we have something lower than 3, 2, we would have 3 squared is equal to 4a minus 7. Then we'd have 9. And this would result in a being 4. Therefore, it has to be less or equal to 18.5.
So the value of 2 would have worked for us because our logarithm can equal to 2, and that's part of this inequality. And we just found out that that will happen when A equals to 4, which is less than 8.5. So we know that it's for the values lower than 8.5. Alternatively, yes.
Well, 8.5.
Less or equal. Yes, good. Okay, so that would be a solution. And we can also examine it from kind of examining the original equation. As A grows, this whole value, does it grow or decrease?
As A grows?
Yes, just what I circled. Would 4a minus 7 grow or decrease?
It would grow.
It would grow. So it gets bigger. It means we need to raise 3 to higher and higher power to get to the bigger number. And that will not work for us because it has to be under 3. So we know it has to be less. So basically the sign stayed the same like it was in the original equation. That's not always the case. If we had the fractional base and say less than 2, if you try to solve this one using the same principle, stating that it's equality, so x is equal to 1/3 squared for the equality, then to get a solution for this expression, in the end, x will actually have to be greater than 1, greater or equal than 1/9, because it was a fractional base, just like we have in inequalities when we divide by the negative. So when you're solving, if you're solving it through the equality, then double check which way will be the solution. And this is ours. Part B, we have this inequality for two logarithms, both of them base 7. What do you think we should do here?
Well, it's kind of like a regular inequality. It is a regular inequality because we have the same base. Therefore, we can just remove it and say 5x minus 4 is bigger or equal to 2x plus 8.
So we know that this inside will have to be greater than the inside on the right side, because the resulting into what exponent we raise 7 will be bigger. Well, the only thing we need to watch for, these are logarithms, and this logarithm is not always defined. For example, x cannot equal to -10, because then this is -54, and there is no power of 7. You cannot raise 7 into any power to get -54, right? I cannot even get a negative result no matter what exponent I'm using, because if I try to use negative exponent, for example, like -100, what does it mean?
You're going to get an extremely small number, but it's never going to be 0.
Because negative exponent means I'm taking a reciprocal of my value. So it can get very, very small, never can be 0. So that's to find the domain. For domain, 5x minus 4 has to be strictly greater than 0. So that's another condition. And for the second logarithm, same story. For the domain, 2x plus 8 will have to be greater than 0. Now we need to solve all 3 of this. So let's start with the first one, and then we will add 2 more conditions that we wrote.
So for the first one, we can subtract 2x from both sides. We'll have 3x minus 4 is bigger or equal to 8.
Okay.
And we can add 4 to both sides. So we'll have 3x is bigger or equal to 12. Or x has to be 4, bigger or equal to 4.
Greater or equal than 4. We can say bigger or greater as more standard. Either way. Okay, so x is greater or equal than 4. That's, we compare the insides of 2 logarithms. Now let's make sure that both logarithms are defined. For the first logarithm, we have this condition. Let's solve it for x.
So let's say x is the smallest possible, so 4. So we'll have 20 minus 4 is bigger than 0.
Wait, 5x is greater than 4, right? We are solving the inequality. Oh, you're checking if this is enough. I agree, yes. So if I just solve it directly, I will get x has to be greater or equal than 4/5, but this is stronger that you were checking. So even if we try our smallest possible solution of 4, it's already good enough for this. All right, good. And how about the second one? Let's do the same way as you suggested. So the smallest possible x is 4. And will this expression be positive?
Yes.
Will be positive. So it's good. Both logarithms are defined when x is greater or equal than 4. So we know that's our solution. We did have to check them, but here they happened both to be just fine.